오케이. 두 분 다 황현진님이랑 안성영님 두 분 다 다른 성능을 올리기 어려웠었다. 네, 많은 분들이 작년 수업 때도 아마 많은 분들이 GRU가 성능이, 그러니까 로지스틱이 GRU보다 성능이 잘 나왔던 것 같아요. 근데 그건 뭐 괜찮아요. 그럴 수도 있습니다. 이 태스크 자체가 그렇게 막 뭐 어려운 태스크가 아니기 때문에, 이 생각을 해보시면은, 이 24에서 48시간 사이에 입원한 사람들 중에서 그 사람들 데리고 첫 3시간만 가지고, 그러니까 첫 3시간만 이용해서 이제 이 사람이 죽을 거냐 살 거냐를 판단하는 거잖아요, 지금. 그렇기 때문에 이 3시간 동안에 일어난 일들이 순차적인 게 그렇게 막 중요하지 않을 수도 있어요. 이 사람들이 죽고 산 건 이제 24시간, 48시간 사이에 일어난 일이잖아요. 근데 그거를 첫 3시간만 가지고 이제 맞춰라 이런 건 사실 첫 3시간을 다 그냥 순서 없이 다 뭉뚱그려도 크게 뭐 상관은 없습니다. 없을 것 같죠? 그러니까 이제 뭐 저도 뭐 뭐 의학 전문가는 아니니까. 근데 생각을 해보시면은, 그러니까 첫 3시간을 그냥 다 더해버리거나, 뭐 이렇게 로지스틱 리그레션 생각해보면 그냥 다 웨이썸 하는 거잖아요. 이제 다 더해도 충분히 성능이 잘 나올 수가 있다. 그리고 다른 성능이 나오기 잘 안 나오는 건 이제 뭐 순차적으로 넣을 때 이제 밸류를 어떻게 할 거냐, 뭐 이런 것들이 조금 이제 테크니컬한 문제들이 있어서 그럴 수도 있고요. 그러니까 애초에 그렇게 꼭 뭐 이게 반드시 GR을 써야지 풀 수 있는 문제가 아닌 거죠. 처음부터 생각을 해보시면. 네, 그냥 연습 삼아서 해보셨다고 생각을 하시면 됩니다. So what I just said is, so the questions from Hyunji Hwang and Song Yong-han was that was more difficult than expected to uh, get decent performance out of GRU compared to getting performance out of logistic regression. And my suspicion is, or my estimation is, that given the nature of the task, which is that we take patients who stayed in the ICU for between 24 and 48 hours. So the patient either was discharged or was dead or died between 24 and 48 hours in the ICU, and we're only taking the first 3 hours as features to predict whether the patient died or not. So, which is a really short amount of time. I mean, 3 hours. The first 3 hours, you don't need my estimation is that you don't need to actually think too much about the sequence of events that happen within the first 3 hours, whether you sum them up or because logistic regression is basically weight summing the features. So whether you sum them up or whether you put the first 3 hour events in sequentially into the sequence model, doesn't make a really big difference. But that's just my estimation. And yeah, a lot of people from the same class last year, I think they also obtained better performance using logistic regression compared to GRU. 성명님, 제가 잘못했을 수도 있는데 로지스틱에서도 피치가 GRU예요. 네, 그렇죠. 그러니까 다르지 않은 거죠. 뭐 떨어지지 않은 것만 해도 뭐 다행일 수도 있고요. 그러니까 이제 그대로 그러니까 로지스틱에서의 피처는 이 순서 없이 그냥 이제 넣은 거고, 그다음에 이걸 순서대로 넣어도 큰 차이가 없다는 게, 그러니까 사람이 죽고 사는다라는 이 사람이 죽고 사는 문제가 첫 3시간을 봤을 때 그렇게 중요하지 않다는 거죠. 그 순서라는 게 그냥 이제 다 백업워드처럼 순서 없이, 그러니까 이제 NLP의 백업워드처럼 순서 없이 그냥 이런 피처, 이제 이런 사건이 발생했다 안 했다 이것만 중요할 수도 있다는 거죠. 특히나 첫 3시간만 보기 때문에. 네. 네, 뭐 그게 답이 될 수도 있을 것 같고요. 그다음 현지님, 혹시 과제 스펙에서 결측치를 단순 조합해버리는 것은 과제 편성 수준을 주신 것일까, 아니면 해스케 데이터에서 다른 것을? 굉장히 좋은 질문인데요. 이 질문이 밸류넘이 없으면은 그냥 이제 없는 취급하는 거냐, 아니면은 그러니까 없는 취급하는 게 편의상이냐, 아니면 실제로 결측치를 함부로 이제 미싱 데이터를 함부로 예측하는 게 성능에 오히려 나쁠 수도 있어서이냐라고 이제 질문하셨는데, 일단은 이 숙제에 대해서는 전자의 성격이 더 강하고요. 그러니까 이제 이거를 밸류 넘버가 뭐 틀리거나 뭐 오류가 있거나 아니면 뭐 스트링이거나 뭐 이런 경우는 이제 제가 다 빼버리라고 이제 말씀드린 거는 그래도 쉬워서 그래요. 그냥 이제 하나하나 그 코너 케이스마다 다 이제 대비해 가지고 코드를 짜고 이러려면 이제 워낙 어려우니까 이제 그냥 그걸 빼라고 말씀드린 건 편의상 그렇게 한 거고요. 그다음에 이제 실제로 결측치를 어떻게 하는 게 좋냐, 이걸 이제 굳이 채워 넣어야 되냐, 그럼 채워 넣을 거면 어떤 방법을 쓸 거냐, 이제 뭐 인터폴레이션을 해야 되는데 이걸 이제 민을 하냐, 아니면 이제 가장 가까웠던 값을 그냥 그대로 복붙을 하냐, 이런 여러 가지 테크닉이 있는데 사실 그 어느 것도 다 완벽하진 않아요, 당연히. 왜냐하면 존재하지 않는 값을 지금 맞추려는 거기 때문에 그거가 이미 하나의 예측 태스크잖아요. 네, 예측 태스크로 맞춘 값을 이용해서 또 다시 그 다음 예측 태스크를 해야 돼가지고 어떻게 잘못하면 이제 오히려 안 하면 못한 그런 뭐 상황이 발생할 수도 있죠. So this question was pretty important. So what Hyunji Hwang asked is that the instruction of assignment, I mean, project number 1 was that if the value number is not a actual number, or if it's like a null or if it's string, then I said in the instruction, the spec in the Google Doc, to just drop that value, just ignore the value and just use the value that is actually a numeric value. And the question from Hyunju Wang was that decision to drop the value, was that for convenience sake, or was it because predicting or filling the missing value is potentially harmful for the prediction performance? And my answer is mostly the former. So dealing with missing value is itself a research topic. So trying, if I had said that to fill the missing value with some advanced technique, then that would have made the project number 1 way more difficult than already is. So it was just for convenience sake. And as I said, dealing with missing value is a research topic of its own. So there are a lot of different techniques, and some techniques, depending on which task you are doing, and depending on what kind of situation you're in, there is no right solution, like one solution for every situation. So you have to, there are interpolation techniques, like taking the average between the consecutive values, or taking the most recent values and copy pasting it, or actually training a new model to actually predict the missing value, or modifying the GRU cell to somehow estimate the decaying of the recent features. All those are really advanced not really, but all those are like advanced techniques that if used incorrectly might be harmful for downstream performance. So that's why I just said to drop the values if it was inappropriate numeric value. 변영재님, 측정의 순서는 환자의 상태에서 다소 독립적인 요인이 많지 않을까요? 같은 아이템 아이디에서 선수가 아니라면 그럴 것 같아서 했습니다. 네, 좋은 말씀입니다. 예, 변영진님, 이제 측정의 순서는 환자의 상태에서 다소 독립적인 요인이 많지 않을까라는 건데, 이제 요번에 다루신 차트 이벤트는 주로 이제 정기적으로 재는 밸류들이 많아요. 그러니까 혈압, 맥박, 호흡수, 산소 포화도, 그다음에 체온, 이런 것들은 이제 그냥 거의 뭐 30분에 한 번, 1시간에 한 번 이렇게 그냥 자동적으로 이렇게 체크가 들어가는 그런 것들이 많기 때문에 그런 것들은 이제 반복 측정인 거죠. 그래서 사실 순서가 중요하긴 한데 말씀드렸듯이 첫 3시간 안에 발생하는 정보들만 가지고 우리가 이제 이용을 하기 때문에 그 3시간 내 정보의 순서가 그렇게 중요하진 않다는 거죠. 이제 이게 만약에 우리가 뭐 23시간의 정보에 23시간치의 분량의 정보를 가지고 이제 우리가 원래 했던 24시에서 48시간 사이에 환자가 이제 죽을 거냐 살 거냐 예측한 거면은 첫 23시간을 가지고, 그러면 이제 정보의 그 순서가 중요하거든요. 당연히 첫 0시간 때 발생한 것보다는 23시간 때 발생한 게 더 중요할 수 있잖아요, 정보가. 근데 그게 아니라 첫 3시간 내에 발생한 건 어차피 우리의 타겟 이 시간대하고 아주 멀기 때문에 어떻게 보면은 그게 이제 그래서 별로 그렇게 중요치가 않을 수 있다는 게 제 생각입니다. 그게 아니라 이제 그리고 뭐 이제 그 뭐 체온, 혈압 이런 정기적으로 재는 게 아니라 특수하게 그냥 뭐 이제 뭐 혈액 샘플을 잰다거나 뭐 소변 샘플을 뭐 가지고 뭘 한다거나 이런 거는 이제 그런 거는 약간 뭐 특수한 케이스니까 이제 그게 뭐 3시간 뭐 2시간 반째 일어났다거나 뭐 1시간째 일어났다거나 1시간 반째 그건 그렇게 중요하지 않을 수 있어요. 형제님 말씀대로. 네, 그렇습니다. 하지만 네, 좋은 지적이에요. 이게 다 이제 어떤 측정치냐에 따라서 다 그게 그 반복 정도의 정보도 다르고 그래서 사실 이제 그 뭐 뭐 혈압이라든가 이런 것들 혈압 이제 체온 뭐 산소포화도 이런 건 너무 자주 측정되니까 사실은 거의 뭐 5분에 한 번 또 1분에 한 번 측정되기도 하거든요. 제가 이제 그 첫 이벤트 그 EICU랑 미믹이랑 헷갈리는데 둘 중 하나는 EICU였는지 미믹이었는지 하나는 이제 5분에 한 번씩 측정이 돼서 저장이 되고 하나는 1분에 한 번씩 측정돼서 저장이 돼요. 그 혈압이나 이런 것들 이거 바이탈이라고 그러거든요. 이제 생체 신호라고 그러는데 혈압, 체온, 그다음에 산소포화도 호흡수, 맥박수 이런 것들은 이제 생체 신호라 그러거든요. 그런 것들은 1분 또는 5분에 한 번씩 측정이 되기 때문에 이제 너무 많이 발생해요. 너무 많이 발생하니까 이제 그거를 이제 롱텀으로 보려면은 그래서 1분에 한 번씩이다. 근데 우리가 뭐 뭐 이 사람의 환자가 ICU에 3일 동안 입원을 했다. 그러면은 1분에 한 번씩이면 도대체 몇천 이게 몇천 개죠. 1분에 한 번씩 60 곱하기 그러니까 하루만 해도 60 곱하기 24니까 1200이잖아요. 이제 하루만 해도 1200 시퀀스인데 그게 3일이면 3600 시퀀스니까 시퀀스 길이가 엄청 길단 말이에요. 3일 만약 3일치를 가지고 뭘 GRU에 넣는다 그러면 이제 그런 경우는 너무 길기 때문에 이제 이거를 버켓으로 잡는 경우도 있어요. 이제 그냥 1시간 간격으로 이제 이게 1분이지만 그 1시간 간격으로 나는 그냥 뭉뚱그리겠다. 그래서 1시간 동안의 평균 혈압, 그러니까 1분 동안, 1분마다 재지니까 이제 60개의 혈압 수치가 있지만, 그거를 나는 평균으로 60개를 평균해서 1시간의 혈압으로 대변하겠다. 그래서 이제 1시간 동안 평균, 1시간 동안 미니멈, 1시간 동안 맥시멈. 이렇게 해서 이제 60개의 밸류를 3개의 밸류로 퉁쳐가지고 이제 이거 버켓으로 짜서 그래서 이제 그걸 이제 시간 단위로 하는 뭐 그런 테크닉도 얼마든지 쓸 수가 있습니다. 만약 더 롱텀으로. 그러니까 이제 우리는 지금 이제 시간 단위, 우리는 3시간, 첫 3시간만 했기 때문에 이제 우리는 그냥 그걸 이렇게 버켓타이징을 안 했, 그러니까 이제 뭉뚱그리지 않았는데 그냥 뭉뚱그리는 것 자체도 또 이제 또 하나의 어떤 전철이니까 이제 뭐 복잡할 수 있어서. 근데 만약에 이제 더 롱텀으로 보고 싶다, 그럼 이제 그런 어떤 버켓타이징 기법을 쓰는 게 좋습니다. 실제로 이제 구글 헬스에서 했던 것들은 뭐 그런 식으로 이제 굉장히 장기간이면은 이런 거를 이제 뭐 개월 단위로 이렇게 버켓타이징을 했었거든요. 이제 그런 것들이 얼마든지 가능하다 이렇게 말씀드리고 싶습니다. 네, 승우님, 처음에 GRE 문제를 해결할 때 임베딩을 사용한 것 말고 교환처럼 타임스텝에 대해 엄청 큰 원합 벡터를 만들어서 배치 단위로 넣어주려고 했었는데 언파일은 저장이 불가능하다. 혹시 테크니컬한 부분이 있어 용량의 교장이 굉장히 큰데 용량이 큰 넘파이로는 이제 원합 벡터로 넘파이 형태로 저장하려니까 너무 커가지고 저장이 불가능해서 테크니컬한 부분에 있어서 용량이 큰 데이터에 대해 저장을 하거나 이런 부분에 효율적인 테크닉이 있을까요? 아니면 접근법이 잘못된 접근법이었나요? 교환처럼이라는 게 무슨 뜻인가요? 교환처럼 각 타임 스텝에 대해서가 무슨 뜻이죠? 강의대로. 아니, 그러니까 강의에서 말씀드린 것이 원합 벡터, 그러니까 이제 임베딩의 아이디들을, 이제 차트 이벤트의 아이템 아이디들이 사실은 하나의 어떤 하나씩 다 이제 원합 벡터로 나타낼 수가 있잖아요. Alright, so this is a bit important, so I'll just rephrase it in English. The question from Ryu Sung-woo was that when dealing with, when trying to train the GRU with one hot vector. So the item IDs, each item IDs in the chart events, they are equivalent to each words, like individual words in NLP. So you have a large vocab size, and so each item ID can be represented as a one hot vector. And if you try to store your one hot vector in a NumPy format, then that would actually that wouldn't fit in the NumPy object because it's too large. So storing GRU features as actually NumPy, like pre-processed multi-hot, one hot, or actually like NumPy tensor would actually take a lot of require a lot of hard disk space, and it probably wouldn't fit in a single NumPy file. So the question was whether there's a better way to do it, or if it's just the wrong. If it's, basically if there's like technically a better way to handle those high dimensional, very sparse features for sequence models, and the answer is yes. So I'm not sure if I said during the lecture that people should store GRU features as one hot vectors. I think during the according to the instruction of the project number 1, I think I said to store them in a string format, because so string format meaning that the item IDs should just be stored as item IDs, or integer version of the item IDs, because you need to convert the item IDs to an integer, and words, like as you're converting words to integers in NLP. So if you store them in string format, and then you don't have to, then you would be, that would be very efficient. 그러니까 제가 인스트럭션 그 스펙에 써드린 대로 뭐 아이템 아이디, 밸류 넘버, 타임스탬프 요 트리플로 이렇게 따다다닥 저장을 하면은 훨씬 더 용량을 줄일 수가 있죠. 대신에 그걸 이제 그렇게 스트링으로 저장한 다음에 그거를 읽을 때는 이제 그걸 다 메모리에 올려놓고, 그 다음에 그거를 미니 배치를 만드실 때만 잠깐 이렇게 그걸 텐서로 변형을 해가지고 그걸 이제 그 GRU 비디오 메모리에다 올리고, 다음에 이제 처리하고, 다음번 미니 배치 때는 또 그 스트링으로 표현된 거를 조금 떼다가 다시 또 미니 배치에 텐서로 바꿔서 또 한번 돌리고, 이런 식으로 하는 게 훨씬 더 훨씬 더 효율적이죠. And I think, I'm not sure if there's a specific or specialized data format for sequence data, but there is one in TensorFlow. It's called a sequence features. So actually, let me share my screen with you guys. Right. So in TensorFlow, there's something called sequence features. Actually, there's due to the update, I think it's now in the Keras, not the TensorFlow. All right, let's go to the TensorFlow version 1. And I think there has been some refactoring, because this is not the one, not the sequence feature that I'm used to seeing. Feature column. Right. Okay, it's feature column serialization. Sequence features, TensorFlow sequence features. Sequence. All right, I'm sorry, I think maybe this is it. No, this is not. All right, so I'm not, because of all the updates, this is not the one that not the features that I'm used to seeing. But in TensorFlow, there is a specialized data structure called sequence feature, which is actually just a sequence of features. So okay, so first of all, there is something called features in TensorFlow. So features is a specialized data structure to store actually just the features. So features is just a key value dictionary. So it's a dictionary. It's a TensorFlow dictionary to be more specific. So just like Python dictionary, there's a TensorFlow dictionary, and the TensorFlow features is just a dictionary for having storing features, and then sequence feature is just basically sequence of dictionaries. So it is a specialized data structure to store, for example, like NLP data sets, something like that. That is by nature sequential. So I'm not sure if there's something equivalent in PyTorch such as sequence features, but you can actually in TensorFlow you can actually store sequence features in TensorFlow record TF records. So that is actually like it compresses the features. So just like zip or tarball, it's Google actually open source something called I forgot the. It's just some compression algorithm. So basically when you store things in TF record, it basically compresses the data set, the features, so you save a lot of space, and that's how you actually use. That's how you save a lot of space. No, but it is a specialized data structure or technique for TensorFlow only. So I'm not sure if there's something equivalent in PyTorch where you store things in like a dictionary format while compressing it. So actually, maybe someone who is more familiar with PyTorch than I am, maybe they can share their opinion. But so yeah, my suggestion is if you have a sequential data with very high dimensional sparse features, don't store them in tensor format because it would take a lot of space. Just store them in their feature ID form. So and then when you load them, you either use embedding lookup or you actually you can use embedding lookup using those integer IDs, or you can just you can convert them into one hot vectors yourself and then convert them into embeddings. That's up to you. Question from Soro. I did not use embedding because I consider item ID as the columns and value num as the values, right? And constructed pandas data frame with that, from which each row represents a measurement at a given time. What do you think about my process? Item ID as the column and value num as the values. I'm not sure how that would work because there would be multiple. I mean, there would be multiple measurements from the same item ID. So I'm not sure how you can treat them as columns. So sorry, my assumption is that you treated everything as a table. So there are like different item IDs become a column, and then within the column there are values. And you can totally do that with logistic regression, where you have to somehow deal with not duplicate, but measurements from the same item IDs, but at different timestamps. So you have to deal with that problem in logistic regression. In GRU, you can just feed them in the temporal order. So I'm not sure how you can do that. How you can use your table-based approach for GRU. You can totally do that with logistic regression. 변현직님, 저는 차트 타임이 동일한 아이템을 하나의 이벤트로 묶어서 백업 아이템 형태를 GRU에 넣고, 네, 그렇죠. 그 피처별로 마지막 측정 값을 이후 입력에도 그대로 유지하는 방식을 썼는데, 피처별로 마지막 측정 값을 이후 입력에도 그대로 유지하는 방식을 썼는데, 그게 무슨 뜻인가요, 형제님? 동일한 시간에 발생한 아이템들은 순서가 없이 그냥 다 더했다, 피처를. 뭐 이런 뜻이신 것 같은데, 피처별로 마지막 측정 값을 이후 입력에 그대로 유지했다는 게 무슨 뜻인가요? 그러니까 미싱 밸류를 계속해서 그냥 쓰셨다는 건가? 그러니까 예를 들어서 1분, 이제 뭐 1분 때에 혈압을 측정했고 1분 30초 때에는 뭐 체온을 측정했는데, 그럼 1분 30초 때에는 1분 때 혈압을 1분 30초 때 혈압에 또 썼다는 얘기예요. 그러니까 다 같은, 매 타임 스텝마다 같은 수의 피처를 넣어주기 위해서라는 얘기인가요? 아, 네, 알겠습니다. 그러니까 이제 무조건 그냥 환자마다 뭐 예를 들어서 100개의 타임 스텝을 무조건 쓰고, 왜냐면 맥시멈이 100개였으니까. 그러니까 환자마다 무조건 100개의 인풋이 GRU에 들어가고, 인풋 타임 스텝마다는 어, 동일한 피처가 계속 들어가는 거예요. 동일한 피처의 개수가. 그리고 이제 피처가 있으면 그 값을 쓰고 없으면 예전 값을 쓰고 뭐 그런 식으로. 그러니까 뭐 어떻게 보면 이제 똑같은 차원의 피처가 계속 매 타임 스텝마다 들어가도록 이제 조절을 하셨다는 걸로 제가 이해를 했습니다. 근데 물론 그렇게 하셔도 돼요. 그러니까 이제 뭐 새로 측정되기 전까지는 이제 가장 최근 값을 계속 넣어준다. 그러니까 어떻게 보면 이제 미싱 밸류를 계속 그냥 더 most recent 밸류로 계속 이제 리플레이스를 해가면서 똑같은 그 숫자를 이제 계속 같은 피처가 계속 들어오도록 타임 스텝마다 그렇게 조정을 해주신 거고, 이제 그거를 이제 그 NP 형태로 저장을 할 수가 있죠, 당연히. 이제 왜냐하면 그거는 매 타임 스텝마다 똑같은 수의 피처를 쓰기 때문에 이제 그런 식으로 완전히 이렇게 3D 텐서화 시켜가지고 저장을 할 수가 있죠. 그래서 NP로 저장이 가능했고, 타볼 건집 압축을 했을 때 상당히 잘, 네, 뭐 물론 그렇게 하셔도 됩니다. 그렇게 하시는 게 뭐 하나의 어떤 이 미싱 밸류를 다루는 방법 중 하나죠. 그러니까 미싱 밸류를 아까 말씀드렸듯이 다루는 방법이 뭐 이제 뭐 앞뒤 재서 평균 내거나 뭐 아니면 뭐 그거 자체를 예측하거나 하는데, 그렇게 가장 최근 값을 그냥 복붙한다라는 것도 뭐 하나의 어떤 테크닉이 충분히 될 수 있거든요. 그래서 뭐 그렇게 하셔도 괜찮습니다. 뭐 성능만 잘 나온다면, 사실 치팅만 하고 성능만 잘 나오면 뭐든 다 괜찮습니다. 그런데 그렇게 했더니 성능이 잘 나오던가요, 변현정님? 네, 뭐 성능에 대해서 뭐 답을 하고 싶지 않으신가 보네요. 네. 다만 3시간 내에 차트 타임 만큼까지만. 이 방식으로도 류승님이 말씀하신 방법과 같은 규모의 인풋 같아서 성능 로지스틱보다 나빴습니다. 같은 규모 인풋이다. 사실 그렇죠. 맞습니다. 같은 규모 인풋이 맞는 게, 어차피 한 타임 스텝당 들어가는 디멘션의 숫자는 똑같으니까. 왜냐면 이제 멀티 하실 거 아니에요. 이제 백업워드니까 원화 대신에 여러 개가 1인, 이제 하나만 1이고 나머지가 다 빵인 피처가 들어가는 게 아니라 매 타임 스텝마다 여러 개가 1일 수가 있는 피처가 들어가는 거겠죠. 그러니까 이제 차원에서는 똑같아서, 류승님 말씀하신 것과 이제 같은 인풋에 그건 맞습니다. 네. 아마 그럼 글쎄요. 근데 류승우님이 더 다양한 피처를 썼던가 아니면 뭐 더 긴 뭐가 썼던가 뭐 그러지 않았을까요? 어쨌든 이론적으로는 같은 인풋 사이즈가 나오는 게 맞습니다. 성능은 로지스틱보다 나빴다. 네, 뭐 그거는 네, 살짝 나쁠 수 있고, 그게 뭐 전혀 이상한 건 아니기 때문에 너무 그걸 신경 쓰실 필요는 없어요. 류승우님 또 다른 질문인데, 예를 들어서 로지스틱 리그레션에서 피처를 만들 때 트레인 테스트 세트 레벨이 아닌 전체 데이터셋에서 출현적이 있는 모든 값을 해석할 피처 리스트를 만들었었습니다. 트레인 테스트에서 출현적인 피처들로만 피처 리스트 만드는 경우도 본 것 같은데, 전자를 하다 보면 지나치게 스파스해지고 성능이 떨어지는 문제가 있긴 했습니다. 원론적으로 전자가 옳지 않나 싶은 생각도 어떤 방식이 오는지. All right, that's an important question. So the question from the last question from Ryusung is that 아니 근데 그게 로지스틱 리그레션에서만 그런 현상이 있나요? 그 GRU하고 똑같은 얘기 아닌가요? 그러니까 모델이랑 상관없이 지금 그 현상은 네네 네. All right, okay. So the question was that when you're trying to train a predictive model, you first have to come up with a feature list of features. So because you have a data set which are patients who stayed in the ICU between like 1 day and 2 days, and you have extracted the first 3-hour window amount of features, and now you have to count how many unique features there are to convert each feature to an integer, right? And in that process, the question from Ryusung is that whether you should actually strictly count you should strictly create a feature list using only the trained data. And so if you do that, then you would be seeing a lot of new features, like unseen features at test time, because if you only construct your feature list using the training set, then there are certain features from the test set that were not in the training set. So those would be all out of vocabulary features, like OOV features. So that you would encounter a lot of OOV cases when you're testing your model using the test set. And that could be problematic. So another way to deal with this is to actually just look at the entire data set, training set, test set combined, you create a feature list. And in that, if you do that, then you would be seeing the entire features, and then you would be converting those features into integers, and then there would be no out of vocabulary problem when you're testing your model on the test set. But the important thing is there are essentially no difference between the two. If you think about it, if you think about it, even if you create your feature list using the entire training set and test set, the features that only occur in the test set. So let's just assume that feature ID is like like 500, like feature integer ID 500 only occurs in the test set, and it is never seen in the training set. If that's the case, then feature ID 500, the embedding vector for feature ID 500 would not be trained during the training phase, because that feature never occurs in the training set. So those embedding vector, the embedding vector for feature ID 500 would be randomly initialized according to some initialization scheme, would be randomly initialized and would stay that way during the entire training phase. So compared to that, and actually treating feature ID 500 as an out of vocabulary, UNC token, in my opinion, there is essentially no difference between the two. So it is weird actually that there are, as I said, there are two ways to create feature lists. One is to base your feature list only on the training set, and two is base your training feature list on the entire training set and test set. If there are performance difference between the two, that is a bit weird to me. 혹시 류정님 이해가 되셨나요? 그러니까 피처 리스트를 만드실 때 트레이닝 셋만 가지고 만들 수도 있고 트레이닝 셋, 테스트 셋 가지고 만들 수도 있어요. 물론 이제 후자는 약간 치팅의 느낌이 있는데, 왜냐하면 우리가 테스트 때 어떤 피처가 들어올지 모르잖아요. 그러니까 당연히 원래는 트레이닝 셋만 가지고 피처 리스트를 만든 다음에 테스트 셋 때 처음 본 피처가 들어오면 그거는 이제 out of vocabulary 또는 뭐 UNK, unknown 토큰으로 처리를 해주시는 게 맞습니다. 그런데 설사 피처 리스트를 만들 때 트레이닝 셋하고 테스트 셋을 모두 다 봐가지고 이제 하나도 내가 처음 보는 피처가 없다, 처음 보는 피처, 이제 unknown 피처나 out of vocabulary 피처가 없다고 쳐도 어떤 피처, 그러니까 테스트 셋에서만 발생하는 피처는 트레이닝 셋에서 한 번도 발생하지 않기 때문에 학습 때 그 피처는 학습이 되지가 않아요. 당연히. 그러니까 한 번도 백프랍이 그쪽으로 가지가 않는단 말이에요. 그 한 번도 발생하지가 않기 때문에 이제 그래서 그쪽 인베딩은 아예 그냥 이제 건드려지지도 않기 때문에 그거를 그 상태에서 테스트 이밸류에이션 해도 성능이 좋아질 이유가 하나도 없습니다. 그래서 성능이 더 좋아지고 나빠지고가 크게 차이가 아예 이론적으로 있을 이유가 없어요. 그래서 성능이 떨어지는 문제가 있다는 게 그게 저는 좀 이해가 그럴 수가 없다는 거죠. 그러니까 전자로 하다 보면 지나치게 스파스해지고 성능이 떨어지는 문제가 있다는데 지나치게 스파스해지는 건 뭐 그럴 수도 있어요. 근데 성능이 떨어질 리는 없다는 거죠. 제 말이 맞나요? 그러니까 성능이 차이가 나면 안 돼요. 그러면 뭐가 잘못된 거예요, 그러면은. All right. So I'm just taking a lot of questions because there aren't a lot of stuff to go through today. So hopefully that's okay with everybody because we're gonna wrap up the interpretability slide today and then focus on the concept embedding on Thursday. So we have some amount of time to focus on the questions from project number 1. All right. So question from Sorrel. According to the item table, so that's the definition table, item IDs are duplicated and different item IDs mean the same measurement. For example, for heart rate has IDs 211 and 220045. How do you deal with that when considering the raw item ID as it is? That's a very good question. So if you have read the Mimic 3 overview or the table descriptions carefully, then you would know that the Beth Israel Hospital. So Beth Israel Hospital is where the Mimic 3 dataset came from. So Beth Israel Hospital, they changed their EHR solution, EHR system between during, I think it was the year of 2008. So Mimic 3 dataset was collected from Beth Israel Hospital from the year 2001 and 2012 or something like that. So it's roughly about like 10 years worth of data. And between, so let's say that it started from 2002 and then ended at 2012. At the year of 2008, the Beth Israel Hospital, they changed their EHR system. So their format has changed entirely. So all the data set from 2002 to 2008, they're following the format called CareView format. And starting from 2008 and then until 2012, the dataset is following the format called MetaVision. So that's why in the item table, there are two sets of item IDs representing the same semantics. So for example, here, as Sora said, heart rate, item ID, for the same heart rate, so it's the same semantic, there are two IDs. One is 212 and one is 20,000 something. So the former is, if my memory serves me right, the former is the CareView format. So when the Beth Israel Hospital was using the CareView format, CareView solution EHR system, they were using 211, 211 to represent the heart rate feature. But when they changed their EHR system to MetaVision, the new item ID for heart rate is 220045. So that is why there are duplicate semantics, and that's not so. It is not the case for all features. So it is the case for chart events. So especially for chart events, the MIT people, when they were out open sourcing the Mimic 3, they were not able to reconcile the difference between the CareView and the MetaVision format. So they left them as it is in the chart events. But for some other tables, like diagnosis or lab events or prescriptions, they were able to reconcile the difference between the CareView and the MetaVision. So they were able to merge the format into a single format. So some other tables are okay, but for chart events, the difference was just too big between the CareView and the MetaVision. So they just left them as they are. So that's why you see those two duplicate feature IDs or item IDs. And the way to deal with them is actually not to deal with them is my suggestion, because the really smart people from MIT, the really smart engineers from MIT people, they must have tried to reconcile the difference between the CareView and the MetaVision, but they just decided it is best not to meddle with chart events from two different EHR systems, and they left them as they are. So there's got to be a good reason that they decided to do that, and hopefully, and I believe them. So I would say if you just leave them as they are, and I assure you that for a single ICU stay, the heart rate so for a single ICU stay, they would be using a single ICU stay. That the record within the single ICU stay would stick to a single format, obviously, because no ICU stays usually they don't span a lot. They don't span for a really long time. So we're the EHR system being changed is it's a macro level change, but ICU stays, they last usually over like several days or so. So for a single ICU stay, the features in the single ICU stay would stick to either CareView or MetaVision. So there wouldn't be a single case where two different feature, like two duplicate feature IDs would be used in the single ICU stays. That you don't have to worry about that. But when we are training an ICU based predictive model, like we are doing in the project number 1, same item, same semantic, same heart rate being represented as 211 and 220045. That could actually be a bit, suboptimal, because we have one semantic heart rate, but they're represented as two sets of feature IDs, 211 and 220045. So if there was a way to merge them together, that would actually reduce the feature space, and that would actually be beneficial for optimization purposes. So in that case, in that perspective, it is suboptimal. It's less than ideal, but I wouldn't try to look at all the features, look at all the duplicate features, and try to merge them by myself. Hopefully that answers the question, Sora. All right. 네. 이제 잠깐 이것도 되게 중요한데, 앞으로 미믹3를 사용하실 분들을 위해서 잠깐 말씀을 드리면, 미믹3가 이제 베스 이스라엘 하스피털에서 병원에서 오픈 소스가 된 건데, 이게 그 연도가 제 기억이 잘 안 나는데, 예를 들어서 2002년에서 2012년까지 이제 데이터를 쭉 모은 거거든요. 근데 이 병원이 2008년쯤에 병원의 전산 시스템을 다 갈아엎어요. 이제 그 전까지는 이제 케어뷰라는 EHR 소프트웨어를 사용하다가 2008년 이후에는 메타비전이라는 EHR 소프트웨어를 사용을 하기 때문에 많이 피처 아이디, 이제 아이템 아이디들이 많이 바뀌어요. 그 중간에 이제 바뀐 이렇게 EHR 소프트웨어를 바꾸면서 피처 아이템들이 많이 바뀌거든요. 그래서 사실 제가 이제 보여드리자면은, 실제 테이블을 가보시면은 여기 인풋 이벤트가 2개 있잖아요. 인풋 이벤트는 이제 이 환자한테 이 투약이나 이런 걸 주사기에 이렇게 꽂아가지고 이렇게 약 넣잖아요. 마취젤 넣을 수도 있고, 항암젤 넣을 수도 있고, 아니면 고통 이완, 이제 진통제를 넣을 수도 있고, 이런 식으로 이제 약을 이렇게 피하에 이렇게 넣는 그런 투약 행위가 이제 다 인풋 이벤트 저장이 되는데, 보시면 CV랑 MV가 있잖아요. 이제 인풋 이벤트 CV랑 이제 여기 가보시고, 그다음에 인풋 이벤트 MV랑 가보시면은 이게 약간 다르거든요. 그 스키마가. 그러니까 CV가 바로 케어뷰 때의 인풋 이벤트 테이블이고, MV가 이제 메타비전 때의 인풋 이벤트 테이블이거든요. 그러니까 이제 이 MIT 엔지니어들이 다른 것들을 다 통합을 했는데, 이런 경우 이제 요런 두 테이블 같은 경우는 도저히 통합을 하는 게 맞지가 않다 싶어가지고 아예 두 시절을 따로 나눠 놓은 거예요. 이제 케어뷰 시절과 메타비전 시절 인풋 이벤트. 이제 그런 흔적들이 여기 이제 아이템, 여기 D 아이템에 가면 여기도 있는데, 이제 똑같은 하트 이벤트가 여기 있네요. 여기 이제 케어뷰 시절에는 하트레이트가 케어뷰 시절 211이었는데, 메타비전 시절에는 이제 220045로 이제 바뀌는 거죠. 이런 경우도 이제 통합을 못한 거예요. 통합을 하느니 그냥 놔두는 게 낫겠다 싶어서 놔둔 거거든요. 이런 경우가 있기 때문에 이런 걸 이제 생각을 해보시고, 이게 도저히 문제가 될 것 같다 그러면은, 이제 나는 이제 미믹스를 이제 다뤄가지고 데이터를 통계 연구를 하시든, 아니면 프리딕티브 모델 만드시든, 어떤 머신러닝 모델 만드실 때 이제 이 두 시절, 이제 메타비전 시절과 케어뷰 시절로 나눠져 있는 게 문제가 될 것 같다 그러면은 그냥 한 시절만 쓰시면 됩니다. 이제 2008년 이전 데이터만 쓰시면은 케어뷰만 쓰시는 거고, 2008년 이후만 쓰시면은 메타비전만 쓰시는 거고, 그렇게 되는 거예요. 그래서 여기 오버뷰에 있으려면 여기에는 없나 봐. 데이터, 네, 스키마 메타비전. 네, 몇 년도부터 몇 년도까지인지는 안 써있네요. 네, 뭐 어딘가에 이제 좀 뒤져보시면 나오는데 특히나 예. 박기훈님께서 찾아보셨네요. 감사합니다. 2001년부터 2008년도까지는 이제 케어뷰를 썼고 2008년부터 2012년까지는 이제 메타비전을 썼다고 하네요. 네. 자, 필립스 같은 경우는 이제 굉장히 이런 이 헬스케어 쪽에 소프트웨어나 이런 솔루션 같은 거 납품 뭐 이제 개발을 많이 하는 회사라서 실제로 EICU가 필립스 솔루션으로 만들어진 데이터를 다 모아놓은 거라서 이제 필립스의 케어뷰가 쓰였다고 하네 2008년까지는. 그래서 하여튼 말씀드린 대로 이제 요 두 개 이 EHR 시스템이 소프트웨어가 바뀐 게 마음에 안 든다. 나는 이제 하나만 쓰고 싶다 그러면은 2008년 전까지만 쓰면 케어뷰만 쓰시는 거고 2018년 이후만 쓰시면 이제 메타비전만 쓰시는 거라서 그 두 개를 뭐 선택적으로 사용을 하셔도 됩니다. 이제 뭐 저도 이제 그렇게 한 경우가 있고요. 네. 이런 것들이 이제 다 이제 어떤 하나하나의 디테일인데 이제 이게 미믹 4로 가면은 제 기억이 맞으면 미믹 4로 가면 이제 이런 문제가 사라져요. 미믹 4는 연도가 어떻게 되나는 그렇죠. 미믹 4는 보시면 이제 2008년부터 2019년까지잖아요. 미믹 4는. 그렇기 때문에 이제 메타비전만 있는 거죠. 그렇죠. 여기 보시면 이제 as long update covers the year 2008 to 2019, Careview clinical information은 이제 더 이상 더 이상 이제 relevant하지 않아요. 왜냐면 이제 2008년부터 메타비전을 썼기 때문에 이제 아예 그냥 딱 메타비전 하나만 가지고 계속 이제 저장을 한 거를 오픈 소스를 한 겁니다. 그래서 미믹 4는 훨씬 더 이제 어떤 데이터의 정보의 representation이 균일하겠죠. 호모지니어스 하겠죠. 그리고 아이템 아이디가 이제 딱딱 써 있죠. D 아이템에서 이제 22만 번 이하는 더 이상 중요하지 않다. 왜냐면 22만 번 이하는 케어뷰에서 사용하던 아이템 아이디들이기 때문에 이제 22만 번 이상만 쓰시면 된다라고 써 있고 인풋 이벤트 수입은 당연히 없겠죠. 케어뷰 시절 인풋 이벤트는 사라졌고 이제 인풋 이벤트 메타비전 자체는 이제 인풋 이벤트로 이름이 바뀌고 뭐 그런 식으로 돼 있습니다. 그리고 마찬가지로 프로시저 이벤트 메타비전도 이제 프로시저 이벤트로 바뀌고 이런 식으로. 그래서 아직 미믹 4가 완벽하게 오픈 소스가 아직 덜 됐거든요. 지금 이게 아직도 베타 버전일 거예요. 제가 1.0이 아직 안 나왔는데 어쨌든 1.0이 나오면 그때부터 우리도 이제 미믹 4를 뭐 마음대로 사용을 해도 되거든요. 근데 그 전까지는 아직은 이제 완벽하지가 않기 때문에 미믹 4 지금 버전 몇인지는 안 써 있네요. 체인지 로그를 보시면 아시겠네요. 1.0 나왔네요. 저번 달 16일에 나왔네요. 미믹 4가. 네, 워낙 뭐 최신이라서 저도 아직 모르고 있었습니다. 이제 딱 한 달 됐네요. 미믹 4 나온 지. 그래서 네, 미믹 4를 쓰시면은 이제 이런 문제 없습니다. 이제 메타비전이나 케어비전이나 이런 거 중요하지 않아요. 이제는 미믹 4를 쓰시면은 메타비전만 있기 때문에 더 이상 이런 문제를 고통받지 않으셔도 됩니다. 그리고 미믹 4의 좋은 점은 제가 이제 몇 번 말씀드린 것 같은데 미믹 CXR이라는 미믹 체스트 엑스레이라는 체스트 엑스레이 이미지, 이제 엑스레이 이미지 데이터가 따로 있어요. 미믹에는. 미믹 CXR이라고. 이제 이건 미믹 4잖아요. 미믹 CXR이라는 데이터셋이 따로 있거든요. 그거랑 미믹 4랑 연동이 됩니다. 그래서 누가 언제 엑스레이를 찍었고 그때 얘가 받은 뭐 프로시저 아이디, 다이그노시스 아이디 이런 것들이 다 이제 메타 정보들 다 갖다 넣을 수가 이제 컴바인 할 수가 있기 때문에 훨씬 더 멀티모달 연구를 하기가 훨씬 좋아져요. 그래서 미믹 4 같은 경우는 이제 당연히 이런 우리가 지금까지 봤던 수많은 테이블들 지금 보시면 데이터 이제 뭐 테이블들 되게 많잖아요. 뭐 페이션트, 어드미션, 트랜스퍼, 뭐 D 아이템, D 마이크로, 뭐 다이그노시스 뭐 굉장히 많죠. 프리스크립션 이제 우리가 보던 것도 다 있고 이제 조금 더 늘어난 거는 이 이머전 이제 뭐죠 응급실 데이터들이 조금 더 추가가 됐습니다. 이제 응급실 테이블들이 추가가 됐고 나머지는 거의 다 동일해요. 그리고 요런 것들이 있고 그다음에 이제 미믹 CXR에서 이제 이미지 데이터 있고 그다음 미믹 웨이브폼이라고 그래서 심전도 데이터도 있고 그래서 굉장히 멀티모달 데이터 성격이 강합니다. 그래서 그런 연구에 관심 있으신 분들은 앞으로는 미믹 4에 익숙해지셔가지고 미믹 4를 쓰시는 거를 저는 추천을 드리고 싶습니다. 이제 미믹 3는 이제 한물 간 거니까 어떻게 보면은 뭐 그렇게 그런 상태입니다. 네, 좋은 소식이네요. 미믹 4가 나왔다는 건 저도 이제 처음 알았습니다. 네. 혹시 뭐 또 다른 질문 있으신가요? 네, 그럼 오늘 뭐 남은 수업을 한 30분 정도 이제 빨리 해가지고 이제 인터프리터블 이제 끝내고 다음 수업 때는 이제 컨셉 인베딩으로 넘어가도록 하겠습니다. 제가 어디서 듣기로는 그 뭐 수업이 너무 쉽다 뭐 이런 얘기도 들은 것 같은데 또 어떤 분들한테는 이 프로젝트 하는데 뭐 너무 오래 걸렸다 뭐 며칠을 뭐 밤을 샜다 이러신 분들도 있고 그래서 사실 뭐 어느 게 맞는지 모르겠어요. 근데 뭐 듣기로는 이제 NLP 수업이 엄청 빡센데 그거에 비하면 쉽다 이러셔서 뭐 그건 좋은 것 같은데 저는 뭐 수업이 너무 빡셀 필요는 없다고 생각해서 근데 생각보다 프로젝트 때문에 고생하셨던 분들이 많다고 들어가지고 그게 약간 의외였어요. All right, so if there are no more feedbacks, we'll just return to the class. So until last time, we covered the model retain, so which is neural attention based sequence model, which is completely decomposable, and we looked at several examples such as this. So the strength of retain was that you could actually accurately calculate the contribution of each code at each time step or each visit in this case, and the sum of their contribution put through a sigmoid or softmax was the outcome, was the prediction score. So that being said, uh, that means that this is basically equivalent to logistic regression. You know, logistic regression is just you sum the contribution of each feature, the correlation features, and then you put them through a sigmoid function. So that's what logistic regression is. And it's the same for retain. It's just that retain is a sequence model, and the contribution of each code they change from patient to patient. This is more individualized model compared to logistic regression, where the coefficients or the contributions are global. They don't change across different patients. That's probably the only two difference between retain and logistic regression. So retain, the essence of retain is that the coefficients or the contributions are calculated or generated by another set of two sets of neural networks, the visit level attention RNNs and the code level attention RNNs. So that's why the coefficients or the contributions change across different patients. So that's the essence of retain. So now we're moving on to, as I said, so there were three approaches in interpretability as far as I'm concerned. One was gradient-based approaches, such as looking at the content filters or something like that, or using grad chems or chem types of visualization techniques. Two was neural attention-based approaches, such as retain or some other naive attention models as well, because they can still indicate the importance of features concerning the outcomes. The third was model-agnostic approach. So we're going to take a look at two model-agnostic approaches. One is Shapley Value, and another is Lime. So we'll start with Shapley Value. So the reason that Shapley Value, or the reason that I'm calling these two approaches, Shapley Value and Lime, is reason that I'm calling them model-agnostic approaches because they can be used for any prediction models. Like if there is a function that receives input and then predicts an output, like probability of mortality or probability of heart failure or whatever, or ImageNet classifier or translation, whatever, you name it. If you have a function, then you can use Shapley Value and Lime to study the importance of each features. So that is why it's called model-agnostic approach. Compared to that, retain, models such as retain, it's a very model-specific approach. The model itself was designed to be interpretable and to be used for outpatient settings or EHR settings. So that is very model-specific. The model was designed from bottom up for that one specific purpose, to make it interpretable. But Shapley values or lines, they are actually, it's more like a post-processing. So you already have a model trained to do some task, some prediction task, and then you can just apply Shapley value or line on top of that to study the behavior of the prediction model. So let's start with Shapley value first. So Shapley value is a really old concept, and it was proposed by some researcher named Lloyd Shapley. It was proposed in 1953, so that's really a long time ago. And the name of the paper or the name of the article proposed by Shapley was A Value for In-Person Games, so contribution to the theory of game. So it is not it doesn't have anything to do with artificial intelligence or anything, because it's, in 1953 there was no AI, or there was only like one AI, which is a chess program proposed by Alan Turing. But anyway, so this Shapley value was proposed as a study related to game theory. So as exactly written here, it's a method for assigning payouts to players depending on their contribution to the total payout. So it's an in-person game. So so there's an in-person game, and they play multiple games. Like let's say that we are playing. Let's play we're playing soccer. We're playing soccer, and if you win, we get $1,000, and if we lose, we don't get anything. And then there are 11 players in the soccer, and we play like 100 games, and sometimes we lose, sometimes we win, and then total payout was, I don't know, we won like 50 times, we lost 50 times, so the total payout was like $50,000. And at each game, 11 players, they must have contributed in different amounts, because some people, like if there's like Messi, then there's like or like just plain the so-so players. So like some players are really good, some players are not really helpful. So we want to divide the total payout of $50,000 among 11 players, and we want to do it as equally as possible. Like the people who has contributed more, the soccer player who has contributed more should get more payouts, and the player who didn't contribute much should not be divided a big cut. So this whole study is related to that. What is the most fair distribution of the payout among multiple players who participated in the game? So yeah, what is the fairest way to penalize each player in the team? So the way to do it is, we're gonna spin this in the heart failure prediction context. So let's say that assume average prediction score was 0.05. So for all, like we apply our model on 100 different, maybe 1,000 different patients, and the average prediction score. So like the score being like these, like HF risk 0.2474. Let's say that average score over like 1,000 different patients was 0.05, and let's say that there are only 4 features. So there are only 4 players, because this is a way to penalize each player in the team. So player are actually features in our case. So there are 4 players or 4 features, which is this person male or female? So this is the gender player or gender feature. And then obesity. So let's assume that everything is binary. So it's either male or female. It's either obese or not obese. It's the patient has hypertension or doesn't have hypertension. The patient has skin cancer and doesn't have skin cancer. So they're all binary features, and there are 4 players or 4 features. And when the average prediction score was 0.05, this particular patient or this particular combination of features, 4 features, achieved 0.35, so 35% score. So how much difference? The difference between this average score and this specific score is 0.3. So this is 3.5 and this is 0.5. So there are 0.3 difference, and we want to know what is the contribution of this guy, this player, or this feature, the obese feature, for making this 0.3 difference. So if the 0.3 difference was entirely due to or thanks to this obese feature, then the payout, the 0.3 payout, should go all the way to everything. All the payout 0.3 should go to obese, because this feature or this player is the sole reason for making this difference, right? But if that's not the case, if like obese and hypertension combined made this difference 0.3, then they should divide the 0.3 difference should be divided between the two. So it's something like that. So basically the concept is like that. So how do we know how much exactly obese feature contributed towards making 0.3 difference? That's what Shapley value is trying to learn or trying to figure out. So the way to do it is actually just rigorously go through all the combinations to see how much, test the contribution of obese in all possible scenarios, or coalition being just different combination of using all the different features. So that would actually require exponential number of trials. So you can see that there are a lot of different situations. So here, I'm sorry. So here you can see that while not, so here, as I said, there are 4 features. So there are 4 players, and in this first setup, we do not care about. So we randomly select these 1, 2, 3 players, and we only while doing that. Oh, I'm sorry. Sorry about the pause. Okay, so moving on. So in the first scenario, what we do is, while randomly sampling these 3 player values, so it could be male, female, hypertension, no hypertension, skin cancer, no skin cancer. While doing that, we so 50-50 times, like 50% of the times we use obese, and 50% of the time we use not obese. So we're testing only this feature. In this case, we are only testing this feature. And then in the second scenario, while fixing the first player to male, we are testing this feature again, like 50-50, like 50% of the time while fixing the first player to male, 50% of the time we use obese, and 50% of the time we use not obese. And then while fixing hypertension, the third guy, so 1, 2, 3, the third guy, while fixing the third guy to hypertension, we test like 50-50 obese and not obese. Again, then after that, while fixing skin cancer, we do the 50-50, and then after that, once we've tried all the fixed cases for individual features, we then move on to, while fixing male and hypertension, we do 50-50. While fixing male and skin cancer, we do 50. Like all possible scenario, all possible like exponential number of combinations, until we explore every single possible scenarios. Then we know that the average difference made by obese in all combinations. So because we are testing 50-50, like what time, so in this case, what's the difference made by changing obese to not obese? And in this case, what's the difference made, what's the contribution of obese and not obese? In this scenario, what's the difference made by obese and not obese? Like we can look at all the different cases, and then we can average them, and then after we've averaged all the cases, then we know the average contribution or average difference made by the obese player in all combinations. And that is the contribution of obese for making the 0.3 difference. So this is probably, I mean, you can think of like how many scenarios we have to go through in order to actually explore the entire feature space to get the average contribution of a single player, right? So this is a very, very rigorous approach. And so the pros and cons of Shapley value is, the pros is, this is probably the best way, the only ideal way to calculate the exact contribution of each player. So actually exact average contribution of each player. It's like, like if we think about this in terms of soccer, what we're doing is we play a lot of games while using Messi and not using Messi. Like we play all different, like maybe million or trillion different games, and then we can see when using messy and when not using messy, we can see how many times we usually win and how many times we usually lose while not using messy. So that is the contribution of messy to the winning of the game. Just like that, we're doing all these combinations. I think there was a question. 그렇죠. 해당 표시는 피처를 이제 그냥 랜덤리 샘플한 거라고 보시면 됩니다. 네. 그리고 이제 그거를 하나로 픽스한 건 이제 그거 여러 가지 이제 시나리오를 테스트하기 위해서 이제 요거 얘네들이 irrelevant 할 때, 이 언더바들은 irrelevant 할 때고, 이제 그 다음에는 요거에 다 irrelevant 게임을 여러 번 해봤으니까 그때는 이제 오비스 나 오비스의 그 영향을 알 수 있잖아요. 그 다음에 이제 메일로 완전 픽스 해놓고 그 다음에 이제 이걸 가지고 또 여러 번 돌려보는 거고, 그 다음에 하이퍼텐션 픽스 해놓고 또 오비스 나 오비스 막 돌려보는 거고, 여러 번 그 각각 n 타임을 하는 거예요. 한 번만 하는 게 아니라 n 타임을 해야지 다 이게 충분히 많은 샘플이 컬렉트가 되니까요. 네, 그렇게 보시면 됩니다. Right, so the cons is, as you can see, the number of possible combination increases exponentially as you linearly increase the number of features. So while you linearly increase the number of features, like 2 features, 3 features, 4 players, 5 players, 10 players, as you increase them linearly, the number of scenarios that you have to explore exponentially increases. So this is actually not a realistic solution, because if you think about what we did with project number 1, ICD-9 diagnosis code alone takes up 10,000 features. So you have to, if you think, like it's like if we think about, so 10,000 ICD diagnosis codes, and assuming the ICD diagnosis codes are all binary features, then you have to explore 2 to the power of 10,000 cases to exactly understand what individual diagnosis codes are, of how what's the effect of individual diagnosis codes towards the heart failure prediction outcome, which is just impossible. So while this is theoretically a good idea when using like really small amount of features, and when you have a really small amount of features, this is a good idea to do. But in reality, especially these days where we don't really care about the number of features, like easily it goes up to like tens of thousands or like hundreds of thousands. This is Shapley value is not the way to go. So, but what we can do is we can approximate. So Lime is actually one way to approximate this kind of this contribution values. So Lime is called, the reason for the name Lime is because it's a local interpretable model-agnostic explanation. So LIME. So local interpretable model-agnostic explanation. And this was proposed by Ribeiro et al. From, if I'm correct, I think it was from University of Washington in 2016 KDD. And the paper was actually, why should I trust you? Explaining the predictions of any classifier. So that's important. Any classifier. That is why it's a model agnostic approach. And this is you can think of this as an approximation of Shapley value. So Shapley values are too expensive, but what if we can locally approximate? So locally approximate, that means that we have a sample. So we put a sample into the prediction model, and then the model being fed the sample will generate or produce a certain prediction outcome, like 0.5 or 0.7 or whatever, some prediction value. So for that specific sample, we can approximate the Shapley values for that specific sample. And how we do it is we are gonna assume that around that for a specific sample, around the vicinity of that specific sample, we can assume a local linear classifier. So here you can see this is the figure. So let's assume that this is a binary classifier. So that the pluses or the pink ones are one class and the blue ones are another class. So the crosses are one class and the circles are another class. And this entire nonlinear complex binary classifier has a decision boundary like this. So decision boundary like this. It's a very nonlinear, weird looking decision boundary. And everything inside this decision boundary is are the crosses, like class 1, and everything outside this decision boundary are circles, the blue, the class number 2. And so if we were to try to if we were to assume that locally, so for example, let's say that I am trying to focus on this specific bold type cross here, this like thick red arrow, red cross here. As far as this specific sample is concerned, we can probably around this, like this specific cross. Let's draw a circle here. Like let's draw a circle. Let's draw a circle here in the neighborhood of this guy, of this guy. We can draw, so we can see that there are how do I draw this? Let me use the blue color. There are 1, 2, 3, and 4, 5, 6, and 7. So there are 7 samples around this center, the center sample, which is our center of attention here. So there are 7 samples, and around using this in the very close vicinity of, where's my, all right, my mouse is all again lost here. All right, I don't know why this is happening. All right, so around based on these 8 samples actually, based on these 8 samples, a linear classifier or linear decision boundary is enough to classify. To classify between this 1, 2, 3 and this 1, 2, 3, 4. So locally speaking, a linear decision boundaries is enough to classify or divide the 2 classes. This is kind of like, Taylor expansion or Taylor series. Like locally, a linear function is enough to approximate a very nonlinear function. Locally speaking, just like that. Locally speaking, nonlinear classifier. Even if we're dealing with nonlinear classifier, locally speaking, a linear classifier is enough to classify between 2 classes. So that is why we assume that there's like a low linear classifier. So in this case, we actually train a linear classifier. So here, if we're focusing on this guy, we sample a lot of neighborhood samples of this guy, and then using those samples, we train a linear classifier. And then we study that linear classifier to see which ones are more important and which ones are not. For example, if we train a logistic regression using these 7, 8 samples here, if we train, so there is a original nonlinear, very complex classifier, but for this vicinity, this neighborhood, we train an additional logistic regression using these 8 samples. And we already know the classes because this is class 1 and this is class 2. So using these very small number of samples around this sample, we train a logistic regression, and then we can study the coefficients of each features using that additional logistic regression, and then we can decide which features was important, which feature was not. So that's the essence of LIME, this paper. So here, let's read this through. So the decision boundary of the original model is nonlinear, but even a simple linear model can well approximate a local boundary. So this here is the local boundary here, the dots here, local boundary. And here we create a bunch of perturbed samples around the given sample. So here, given this sample, we can create a lot of fake simulated samples. For example, if this guy had blood pressure 95, then we can actually create a lot of different fake samples, like blood pressure of 96, 94, 95.5, 96.5, 94.5, something like that. A lot of perturbations around here. And we actually do know the identity or the class of those fake features or simulated samples because we do have original models. So when we have perturbed samples, we can create a lot of perturbed samples, and then we can put them into the original model to know to get the class class output or the class identity of those perturbed samples. And then once we have a lot of perturbed samples, we can train a linear explainable classifier using those samples. So we can create like million different fake samples around this vicinity of this, around this red guy here, around a lot of different perturbed samples here, like maybe millions or trillions, whatever. If you have a lot of amount, if you have a lot of time, you can train, you can create like as many fake samples as possible. And then we do know their class identity. Then using those samples, we can train a linear classifier and study the samples. So this is one example using a text. So this is an email classification classifier. So it's based on whether the email is about Christianity or atheism. So it's a binary classifier. So given an email, this is, I think, I'm not sure why there is a task here, but this is from some task or some open source data set, NLP data set, and it's a binary classification. Given an email text, try to classify whether this is about Christianity or this is about atheism. And there are a lot of different, so basically this is text, so there are a lot of different, like maybe like thousands or tens of thousands or hundreds of thousands of features, which are just individual words. So here, there are a lot of words, and some words contribute more to atheism, and some words contribute more to Christianity. So purple bar contributes to atheism, and green bar contributes to Christianity. Let me actually clear this drawing here. So here, the document here is right like this. So this is the whole email text, and the classification outcome was that this is about atheism, and the prediction was correct. So prediction is correct. So this was about atheism. I'm not sure why this is about atheism though. Well, I mean, we can at least say that this is not about Christianity. 이제 뭐 기독교나 개신교에 대한 글은 아닌 것 같잖아요, 딱 봐도. 이제 그렇다고 그래서 이게 이제 무교에 대한 게 그런 건 아니고, 제가 보기에 이제 기독교냐 아니냐 그냥 그 두 개예요. 이제 whether it's a Christianity or not. 그러니까 이제 그냥 binary classification이고. 근데 이제 여러 가지. So there are a lot of words here. There is a word like from, PolD, vertex.com, Pol, Durban. These are like individual features in NLP, and you can see that some words contributed more towards atheism. Some words like anyone, this, through, they contributed towards more to Christianity. God, mean, and Koresh contributed more towards atheism. Interestingly, I'm not sure why God, G-O-D, was contributed towards more towards atheism. I think this is because they were all capital letters, like all uppercase letters. I think in usually like, holy texts like Bibles, God is written in capital G, lowercase o and lowercase d, but in this case it was all uppercase God, so that's probably why it's all contributed towards atheism. And the way they perturbed this was to perturb emails by words, like like they can change .com to .net, or core to boy, or whatever, like, or set 8 to 7, something like that, just adding words or deleting words or replacing words, something like that. So yeah, I think that. So yeah, this is one example of actually studying. So the important thing is this contribution is only relevant to this guy, because this is based on local approximation. So for this specific sample, we trained a specific local linear approximator, and that local linear classifier says that this guy contributed towards atheism. So if we're talking about some other document, this contribution no longer works because this is local approximator. So that's what you should keep in mind. I think there was a question. 샘플링을 어떻게 하면 정확히 디시전 바운더리 분분된 로컬 샘플들만 뽑을 수 있나요? That is a good question. So when we're creating a lot of perturbed samples, what is the best way to do it? What is the best way to perturb or obtain perturbed samples to get samples that accurately describes the linear local boundary? And I'm not. The answer is I don't know, because it depends on the modality of your input. If it's all continuous, for example, if it's like heart rate, respiration rate, body temperature, blood pressure, then it is easy to perturb them, because you can actually just add Gaussian noise on top of those numeric values. So in that case, it's very simple. But if we're talking about NLP, then how do we perturb the words? That's actually, it takes a bit more thinking, because if you randomly delete words or add words, then it would drastically change the semantics of the document. So the best way to perturb NLP document is to actually is to change words that have to the words that have, like, replace words with really similar words, like, you know, like here, organization could be changed to like entity or company, something like that. Like if you change organization to like church all of a sudden, then that would drastically change the entire meaning of this document. So that's not a good idea. So yeah, this so the answer to Chungyong Lee is that it depends, and some modality takes a lot of, like, you know, thinking, and some modalities not. Yeah, for images, it's rather easy because you can change the color. You can actually, you know, rotate, or you can crop. There are a lot of data augmentation techniques used in self-supervised learning in computer vision in computer vision fields. So I think the trickiest case is probably NLP, because it's just, there are a lot of semantics in the NLP. And the last example is images. So here, they trained in inception. They have an inception model for ImageNet. So it's like 1,000. There are 1,000 classes. So it's a 1,000 way softmax classifier using inception model, and then trained on ImageNet. And then the important thing about this is you need to have a feature in order to use line. You need to come up with a feature. You need to be able to represent each sample as a set of features, and then you need to perturb those features to get the fake samples around our target sample. So in that case, how do we do that with pixels? The way they did that is use something called superpixel. So superpixel is basically, you know, you cluster each based on this image here, based on this pixel, you cluster the pixels into, you divide the cluster, you divide this image into like several different, you know, superpixels. Like, so for example, here, this is a single cluster. So this is a single cluster, and this is a single cluster, and this is a single cluster, and this thing. So the way they come up with this cluster is using something called superpixel, a patch of, so superpixel is a patch of pixels with common characteristics, like the characteristics being like pixel values, pixel intensities, the brightness, and something like that. So you can break this, you can shatter this image into, like, you know, 100 different pieces, or maybe 1,000 different pieces, and the way you shatter them is based on, you want to shatter them, or you want to divide them into clusters with similar characteristics, and the characteristics are intensities. So like this is like a dog face, and this is some other thing, and this is some other things, you know. And then they perturb images by superpixels. So perturbing them using, you know, different pixel values, or different intensities, or different brightness, or different contrast. And here, because this is ImageNet, there are 1,000 classes. So here, this is the original image, and when you push this image into the inception model, there are 3 classes. I think this model predicted 3 classes. So 1 is electric guitar, 2 is acoustic guitar, and the 3 is Labrador. And we can actually look at local approximate. So we can train a local approximator, and then based on electric guitar outcome, which contributed the most, and this guy contributed the most. Here, this set of superpixels contributed the most to electric guitar class. And concerning with the acoustic guitar outcome, these superpixels, like here, these pixels, or these features, contributed the most for acoustic guitar outcome. And these 2 superpixels, or 2 features, or 2 players, contributed most towards getting the Labrador outcome. So you can see that they are working pretty okay. Like, I mean, I'm not sure why this is electric guitar, but I don't know. That's what the model thought. So based on this one sample, because this is a local approximator. So based on this one sample, using a lot of perturbations. The model thought, the linear model, the linear explainable model thought that this was concerned with electric guitar. I'm not sure what this 기타 통이죠, 우리나라로. 기타 통은 이제 아쿠스틱 기타로 연관이 있고, 그 다음에 요거는 this face was most relevant with Labrador. So it is working pretty nicely in my estimation. All right, so yeah, this is the end of the model agnostic approach. So we took a look at Shapley value and the approximation method line, but there are follow-up methods like deep I think it was deep Shapley value, and which was like trying to approximate the Shapley value using deep learning model. So that probably is a bit more advanced than LIME, but LIME works pretty okay. LIME is a very robust model, and it has a lot of citations. It is a very nice, very like clever way to approximate Shapley value. So it's if you have a non-computer vision model, non-image model that you need that is not attention based, and you still want that to be explained, then you can think you can. Yeah, I suggest that LIME can be a good candidate in that kind of situation. Okay, all right. So this is the end of the class today, and then on Thursday we'll go to concept embedding. If there are no more questions, oh, there's a question. There's okay. Integrated gradient are 심플하면서도 강력하다는 그룹 에피소드인데요. attention vector 사용할까? So integrated gradients are actually gradient-based methods. So they are not the same as attention mechanism. Attention mechanism, as I said, in the I think it was maybe two classes ago, or maybe one class ago. Attention is not actually correlation. Attention is just indication of which feature was useful for making the outcome. So because on top of the attention layer, there are a lot of nonlinear layer following the attention layer. So those are, even if some feature got a lot of attention, doesn't mean that would actually survive throughout the nonlinear layers that comes after the attention mechanism. So attention mechanism is more or less just a bit more like for fun. It's like trying to estimate what might be going on inside the model, but it's not really a complete explanation. Compared to that, integrating gradients are actually more solid way to explain what is going on inside the model. So if you want a bit more rigorous explanation, you should definitely use integrated gradient rather than attention mechanism. Attention mechanism is a bit more, yeah, in my estimation, attention mechanism is not that rigorous. It's a bit for fun. It is better than nothing, but I wouldn't say it's a complete explanation. Yeah, I suggest that you read the paper called "Attention is Not Explanation" and the follow-up paper "Attention is Not Explanation." Why some people think that attention is an explanation, and why some people think that attention is not explanation. So if you read the paper and then compare that with any integrated gradient, you might have a better idea. Okay, cool. That was a very good question. All right, so if there are no more questions, we'll end the class today, and I'll see you guys this Thursday. Thank you, Bobby. Thank you, guys. Bye-bye.